are design patterns. So design patterns are basically best practices, right? So we've been doing machine learning now in production in a lot of different organizations for over 5 years at this point. And so we've built up over time this repository of what are good ways to solve specific problems. And many of these things have names, and providing names to best practices allows us to reach out for them very confidently. So that's what design patterns are. They're formalized best practices for common problems that arise in all kinds of software systems. And the machine learning design patterns, like in this book, we have 30 design patterns that we cover that go through the entire life cycle of an ML project, from how to represent data to how to get explainable AI at the end of the design process. So what we will do in this talk, as I said, is that we will basically cover 3 of those design patterns. Each of us will pick one. So the one that I'm picking is the second design pattern in the book. It's an embedding. So what exactly is an embedding? To understand that, let's think about a typical ML problem. Let's say we want to recommend movies to customers. How would we do that? Well, we basically have a bunch of customers, 10 million customers. We have 500,000 movies, and we basically have ratings by those customers for a few of those movies, right? The movies that they have watched. So given this, what do we want to do? We want to basically suggest movies to customers that are like the ones that they have liked in the past. Okay? So one way that we could do this is that we could basically say, okay, let me organize the movies by some sort of similarity measure. So we could do the average age of viewers with Shrek on the left-hand side is for kids, and Memento on the right-hand side. It's kind of dark and it's very adult-oriented. And then we arrange the movies by that dimension, and then based on that, we could basically then say, if you tend to like kids movies, here's more kids movies that are there for you. But of course, as you can see, but that one dimension isn't very good. It'd be good to actually organize it by multiple dimensions. So let's say we have a second dimension, which is the amount of ticket sales of that movie. And then we basically have at the bottom, we have the art house movies, and at the top, we have the mass production movies. And now we basically have 2 dimensions. And you can basically think about extending it so that you have n dimensions, right, or d dimensions, where you basically have your input, you have your movies, you have 500,000 movies. So your input has 500,000 dimensions because you're going to be one-hot encoding the movie. So you take that and you do dimensionality reduction into a d-dimensional point. Of course, we could give these access names like blockbuster and art house movies and children's movies and adult movies, but we don't have to, right? What we could do is that we could basically take these coordinate points. So these coordinate points are what we're calling the embedding. So Shrek, for example, is -1 because it's for children. It is 1 because it's for blockbuster, and that's the embedding, right? So we could basically take this embedding, but the access do not have to have names. The question is, how do we get these access, right? The cool thing is that you can actually learn the embeddings from data. So given the movie, as you know, it'd be one-hot encode the movie, so the dimensionality is 500,000. We can go ahead and we can represent that input that we have, and we can train some kind of a model to get an embedding. The question is, what kind of a model do we get, right? So that in this case, we are training an embedding so that we get a 4-dimensional embedding. So you will also hear it being called a latent factor or a latent vector. Well, one way that we could do this is that you could train your model where you basically have your one-hot encoded data, and you can pass it through the dimensionality that you want. So in this example, we're trying to learn an embedding of an image. And what we could do is that we could take the raw image, all of the pixel values at the bottom, pass it through a 3-dimensional embedding, and that's what gets used in the rest of the model to basically train a classification system. At this point, then, this 3-dimensional embedding contains all of the information in the image that is relevant to classifying that image. So you can learn an embedding. So the way we create an embedding is that we need a learning task. As long as we have a model that we can train, we basically have an embedding that we can learn. Okay. So we one-hot encode the data, we pass it through an embedding layer, and we train a model. That embedding layer basically is a dimensionality reduction of that entire large, sparse input space that we have. Okay. So the question then becomes, how do we get these learning tasks? The problem, of course, with training a model like this is that we will need labeled data, right? Normally, we do supervised learning. We will need labels, and labeled data is very expensive to create. So the nicest thing is that if you can create an auxiliary learning task where the learning program is actually, you don't have to spend too much time and effort creating the labels. So when we do embeddings, we always look for auxiliary learning tasks where we don't need to have labeling, where we can use then a lot more data. So we're very familiar with this when we look at word embeddings. We basically go take all the books that we have, and we basically take sentences out of those books, and we say, here is the context. The cat sits on the, and make it predict what the next word is. The cool thing is here, there's so much labeled data around because we don't have to actually do anything manual to do it. And the nice thing also is that this embedding that we create is very general. It actually captures the information content that is relevant, right, to predicting the next word. It's not about a very specific kind of text classification. So this is basically the word-to-vec idea. And you basically have a variety of these learning tasks. So for images, the auxiliary learning task that's often used is an autoencoder. The idea is you take your image, you basically one-hot encode it, you pass it through a set of convolutional layers and a set of upsampling layers, and then you basically try to reconstruct the original image back. And in between, you basically have that bottleneck layer. And in this case, you basically get a two-dimensional embedding of the original image. The embeddings, if you do them right, if they're properly regularized and so on, the result of the embedding is such that very similar items are close to each other. And you see this here in the left-hand diagram, where all the reds here are all 9s, and all of these things are close together. All of these are 1s, and these are close together. And nearby items are similar to each other. So these are all the 9s. These are all the 4s. And you can kind of think about how 4 and a 9 basically differ only in the top curve. And the embedding has basically recognized that and put those things close together. It's also possible to do arithmetic and vector arithmetic. Like if you take man and woman, you say, what do I have to do? How much do I have to add to man to get to woman? You add the same thing to king and you can get to queen, and so on. So vector dimensions have meaning, similar items are close to each other. And now, once you have your embedding, you can now use this property in amazing ways. Like, remember, I started out talking about embeddings, talking about movies and recommending movies. Well, this is basically how you recommend songs that are similar to each other. So when Spotify basically gets a brand new song, how do you basically recommend that song? It's not, nobody's listened to it ever before. One way to do that is to look at the kind of sounds that it contains and use that to find similar songs and say, if you have liked slow jazz in the past, you will like this song, right? So you can basically use the embedding of a song to basically find similar songs. You can also cluster embedding vectors. So in this case, I'm basically taking the embedding vector, which is a 50-dimensional vector, and clustering it. And then in this case, what we're doing is I'm clustering images that we get from weather images. And I basically clustered them, and it turns out that in the US, there are like 5 different weather patterns because I asked for a cluster of 5. So take all the weather forecasts that have been done over the US over an entire year. And of course, living in Seattle, it's kind of funny that all 5 of these clusters have rain in the Pacific Northwest. So it rains all the time in Seattle, and it shows up in all 5 clusters. And with that, I will turn it over to who's talking the multi-label.
Yeah,
Mike. Yeah, go ahead.
Okay, so
I'll move the slides for you.
Oh, okay, cool. So I'm going to talk about the multi-label design pattern, and this shows up in the 3rd chapter when we're discussing problem representations. So next slide. So oftentimes when you're building a classification model, you have a single label associated to a single training example. So for example, if you're classifying what's in an image, you have a picture here. and you have a label of either being it contains a cat, a rabbit, or a dog. Next slide. And in doing that, if you've ever built a multi-class classification model like this, you've used a softmax activation layer on the final layer of your model, which just says you determine probabilities for each of the following labels of the image. So a softmax, it normalizes your probabilities so they sum to be 1. And in the previous example, we saw that this model is like 89% confident that this image contains a dog. Okay, next. And in some cases, you may want to let a single training example be assigned to more than one label. And this is what the multi-label design pattern is suited for. So for example, in this picture, the image contains both a rabbit and a dog. And so you want to be able to have both of those labels on a single training example. Next. An example from text might come from something like this toxic comment classification challenge that's on Kaggle, where Wikipedia comments have been labeled by human raters for toxic behavior. So any one of these comments is labeled as containing either toxic, severe toxic, obscene, a threat, insult, or identity hate. Next slide. And so, not surprisingly, this is a good case for the multi-label design pattern because a single comment text could have more than one of these different labels. And the way this looks like when you're building up your data set is you would just be multi-hot encoding those labels, those possible toxicity labels for each of the comments, the way you see below. Okay. So the way you work with this when you're building these models is you don't want to use a softmax layer like we saw before. Instead, you just want to use a sigmoid. So a sigmoid is a nonlinear continuous differentiable activation function. It takes the outputs of each of the neurons beforehand, and it squashes the values between 0 and 1. And in the multi-label design pattern, it's acceptable to have the output array not sum to 1 like we had done before like we had seen before with the softmax, because now what we want to be able to do is for every one of the output labels, we want to be able to have some probability threshold or some probability saying how confident our model is that that image or that example fits that label. Okay, so maybe next slide. Okay, so in the book, again, we've broken things down in terms of patterns within the different parts of the ML lifecycle. And we also have a lot of code, and there's a GitHub repository associated for many of the patterns where you can see that pattern in action. And so for this multi-label design pattern, what we used was a data set consisting of Stack Overflow titles and then the tags of which that Stack Overflow question is related to. So you may have some title, and the tags would be something of either that question is related to Pandas, TensorFlow, Keras, scikit-learn, or Matplotlib. And in the bottom block, you can see how the code is written to incorporate this multi-label design pattern and using the sigmoid activation function. So if we just read the code there, it's like we're setting up a sequential model. There's a few dense layers. Note that the activation functions in the dense layers within our network, we're using the relu activation function. But for our very final layer of our model, we map it to the number of tags, the dense layer that maps the number of tags. In this case, number of tags is 5. And here what we're using is a sigmoid activation function so that we can be able to choose more than one of those possible labels. Okay. Oh. I think, there you go. Okay, so one other thing to keep in mind when you're choosing your, when you're working with a multi-label design pattern is how to choose a loss function. So we saw before when you're working with a multi-class classification, you'll use a softmax and a cross-entropy loss, and that's oftentimes referred to as just a categorical cross-entropy. When you're using a multi-label classification, like I said before, you're going to be using a sigmoid activation function, and for that, when the loss you should use is a binary cross-entropy. So again, just to follow off the code we had before, you can see this in the GitHub repo if you want to take a closer look. When we're compiling that model, we choose the binary cross-entropy as a loss. Okay. Another thing to keep in mind when you're working with the multi-label design pattern is how to interpret or how to parse your sigmoid results. And what I'm referring to here is the use of a threshold of some sort. So for example, if we have a Stack Overflow title that's like, what is the definition of a non-trainable parameter? It goes into our tag classification model. You want to be able to determine some threshold to say, okay, based on this threshold, we will assign that label to that, assign that label to that question. And so, as with any classification problem, there's a lot of care and thought you have to put in to determine what a good threshold is. But here you can see, like, choosing a threshold of say 70%, we can say, okay, that this comment or this Stack Overflow question would be tagged as being pertaining to Keras and TensorFlow. Next. So a good rule of thumb when choosing what a good threshold would be is it often depends on the use case. Like if you're trying to determine tags for a Stack Overflow question, then maybe 70% is good enough. But if you're dealing with something maybe in the health profession, maybe you want to have a higher threshold. It's also possible that different classes or different labels could have different thresholds. So a good rule of thumb that you can keep in mind when you're applying this is you can set your threshold for a certain label to be the number of specific tags over the total number of examples in the data set. So here, number of specific tags means you would look and see, okay, how many of my training examples contain only the term Keras or the only tag Keras. That's my number of specific tags, that label, and then divide that by the total number of examples, just to make sure that what your model is predicting is better than just guessing what it would be from the data set itself. Another thing to keep in mind with this is, in terms of like data set considerations, is like the coverage of your labels in your data set. So for example, if you're looking at the Stack Overflow problem again, and you look at say the labels for Matplotlib and Pandas, if you don't have a lot of coverage of the label for Pandas, the tag for Pandas on its own, then you might want to take some care into massaging your data set or finding more examples that do have just that, only because your model is going to suffer in being able to determine like what makes a Stack Overflow question pertaining to just Pandas as opposed to Pandas and Matplotlib, etc. So just like the normal kind of considerations you want to take into account in terms of balanced data set for a typical classification model, it's a little bit more nuanced when you're dealing with multi-label. Okay, next slide. Another thing to keep in mind are hierarchical labels. So some of you may have come across the ImageNet dataset. It's a popular image classification dataset. It contains thousands of labeled images, and it's used as a starting point for a lot of deep image modeling. All the labels used in ImageNet are hierarchical, meaning you have an image of a husky, but it has various labels along the way saying it's a mammal, it's placental, it's a carnivore, it's a canine, it's a dog, it's a walking dog, it's a husky. And there's different ways you can approach, when in some sense, these are multi-labels for a single training example, right? So it fits within the multi-label design pattern. And there's two approaches that we discuss about how you can handle hierarchical labels. One is to use a flat approach. So you just, you put every label in the same output array, regardless of the hierarchy, making sure you have enough examples of each example in the leaf nodes. And another technique you could use is the cascade design pattern. So Lax showed this an image earlier in the slides about how a lot of these patterns are related to each other. And you'll see that in the book. We try to explain like how a lot of the patterns relate to each other. And this is a good example of how we have a section on the cascade design pattern, and you can think about that in terms of the multi-label design pattern as well. Here, the cascade design pattern would say you build a series of models, and you predict, first you have your first model predicting, if that's a mammal, and then placental, and then carnivore, and it's a cascade of multiple models. Okay. So the multi-label design pattern is also useful in cases where the input data has overlapping labels. So for example, suppose we have an image model that's classifying clothing items for a catalog. One labeler may label an image of a skirt as a maxi skirt. Another identifies or labels that same image as a pleated skirt, and both those labels are correct. So you wouldn't want to use a typical multi-class model label in this case, because you'd have one image that has two different labels, and it just confuses your model. So one way you can accommodate that discrepancy in the labels, or that these two differing labels, is by using a multi-label design pattern, where for a single image it gets labeled as both a maxi skirt and a pleated skirt. And then lastly, one other thing to keep in mind as an alternative is this one versus rest approach towards of using multiple models. So thinking back to our Stack Overflow example that we saw before, we have a single tag classification model that was determining whether a Stack Overflow question had those tags of Keras, TensorFlow, Matplotlib, etc. Another way you could approach that is by building multiple models. So you take that same data set and you can create your labels and train models, just a Keras classification model. So does this question pertain to Keras, yes or no? And so in that case, we go from having a multi-label model to having multiple models that would each predict just a binary classification. Does it contain that tag or not? And that's it for multi-label.
That move to
Cool.
Sara.
Thanks, Mike. I'm going to go pretty fast to make sure we have time for trivia at the end. So model versioning is the 27th pattern in our book out of 30 patterns. You can go to the next slide. You can click once more. So building production models is an iterative process. So once you deploy your first model to production, you're definitely not done. You need to keep iterating on it. And model versioning, this pattern helps you, provides a framework for how to handle updates to your model. You can go to the next slide. First, I'll talk about some of the reasons you might want to update your model. One of these is concept drift. So this is the idea that the target variable, the meaning of the target variable or your prediction task changes over time. So this example on the slide could be applied to both text and image models. So, previously the word troll was associated with this cute little doll. Now when people hear the word troll, they associate it mostly with internet trolls. Same for the words cell and cloud. So you want to make sure that your model's up to date and that your prediction task is still accurate. You can go to the next slide. Another reason you would want to update your model is because of data drift. So data drift refers to the statistical properties of your underlying data or your features changing. So one example is, let's say you're building a model to predict some sort of flight trend. And here we can see a graph of how flight trends have changed over a 15-year period. So if you train a model on data from, let's say, the first 5 years of this, it might do a decent job at predicting flight trends in 2010, but probably wouldn't be so accurate predicting flight trends today. So you need to be constantly updating your model to make sure that it's still performing well. You can go to the next slide. So there's lots of reasons that you might want to update your model. We talked about concept or data drift. You might just have new data. So maybe you're building a model to predict whether or not someone will make a purchase of an item they added to their cart. And you have 9 months of data available, but then suddenly you have an additional 3 months. So you want to update your model and train it on that new data to capture seasonality. Maybe the underlying framework you're using has changed. So maybe you're using TensorFlow and they've updated the version. And you want to take advantage of some of those new TensorFlow features for performance benefits. Your end users might request a change to maybe your model's output format. And you might also have a new data schema. You can go to the next slide. And you can click twice, I think. Yep, so the model versioning pattern handles many of the reasons why you'd want to update your model. And then a few of these can be solved with other patterns, which I'll talk about briefly at the end. So we can go to the next slide. Before we get into the pattern, I just want to talk about 2 types of model users. So just to break this down a little bit, the first type of model user is an application developer. So these are people that are using your model service to get predictions, maybe calling your model's endpoint, and then surfacing those predictions to end consumers, which is the second group. So these are people that are benefiting from your model's predictions. Maybe it's somebody that's using a shopping application to get product recommendations, or it could even be a doctor that's using a model to generate predictions on x-rays. You can click once. So the model versioning pattern focuses mostly on the first category of users, application developers. So that's what I'm referring to in this case. So what is the model versioning pattern? The model versioning pattern recommends using a managed service to deploy different versions of your model as microservices to different REST endpoints. So roughly what this looks like is you have your data scientist, your ML engineer team building the model. They have the model internals. They deploy that model to different REST endpoints. So each version of the model is deployed to a separate endpoint. Then the application developers on the other end ping that endpoint and then choose how they'd like to surface those predictions to end consumers. And you can go to the next slide. So some important benefits of model versioning: it allows for backwards compatibility. So instead of just altogether replacing the production version of your model that's deployed. This allows you to deploy a new version, and then if certain clients want to still use the older version for whatever reason or take time to migrate, that version is still online. It allows for fine-grained performance monitoring, so you can see how different versions are performing. Maybe you want to deploy different versions to different machine types. Related to that point, you can do A/B testing. So maybe you upgraded your model to a new version of TensorFlow, which gave you some added benefits, and you want only to serve that to 5% of your users while keeping the other 95% on the previous version. Model versioning allows for that. And one of the most important benefits I see is that versioning decouples the model from the application front end. So you can go to the next slide. So what I mean by this is you have your data science team. This is just a few examples of why you might want to deploy multiple versions. So maybe you start with an XGBoost model, then you switch to TensorFlow, and then you create a higher accuracy version of that TensorFlow model. Rather than the data science team having to explain to the application developers, hey, this is the exported file format of my model change from .bst for XGBoost to TensorFlow's model format. This is how you have to now call the model. The application developers don't have to worry about any of that. So you, as a data scientist deploying a new model, say I've deployed a new model, the new endpoint is v2. And then the application developer just needs to change the endpoint that they call to access that model without having to worry about how the internals have changed. You can click twice, I think. Once more. Yeah, so all they have to do is change the name of the endpoint they're calling, which is why versioning your model can be really handy. Next slide. One alternative to this, there's a few alternatives we walk through in the book. I'll just talk about one here. So this is specific to TensorFlow. So TensorFlow has this concept of serving functions, which are functions called signatures that you create when you export your model for serving. Most often, you'll just have one signature called the default, but you can absolutely have multiple signatures if you want. So in this example, we have one model signature that's just the default that returns only the model's prediction, but maybe you want to have another serving function that returns the prediction with some explanations, maybe feature attributions. So you create both of these with one model version. They're both deployed to the same REST endpoint. You can go to the next slide. Why might you want to use this? So if you want to continue maintaining multiple versions over time, this can be useful, whereas with model versioning, the thought is typically that you would deploy a newer version and encourage people to move to that version over time. With multiple serving functions, you're maintaining multiple versions of the model over time. This could support different input formats. It might even save processing time. If let's say you have a text model and some of your clients are able to send the embeddings, the pre-processed embeddings to the model directly, you could have one signature for that. And then maybe some clients can only send raw text. And then you could have a separate serving function for that. You can go to the next slide. One caveat to keep in mind when you're looking at this pattern is thinking about whether you should create a new version or a new model altogether. The rule of thumb we typically recommend is that if your prediction task is changing or if the new version would break existing clients, instead create a new model. So just a quick example of when you would do both. So let's say we're building a model to predict flight delays. We start out with a regression model that predicts the delay in minutes. So it outputs a numerical value. And then the clients that are using this model say we classify delay as 15 minutes or more. So we'd rather the model just return, is it delayed, yes or no? In this case, you can click once. In this case, you'd want to create a new model altogether because your output format is changing and this would break anyone that's pinging your model. In the second example, you can click. We keep the regression model, but we simply update the model on new data. So the output format isn't changing. It just is hopefully becoming more accurate. So in this case, we can just create a new version. And then last slide, you can click a few times. Just a quick note on how this pattern relates to some other patterns in the book, plug for some other patterns. Continued model evaluation can help you understand when you need to implement model versioning. The pipeline pattern can help you automate versioning. So let's say that you want to create a pipeline that handles automatic retraining of your model and then uses some conditional to determine whether you should deploy the newly trained version. Bridge schema is an alternative to model versioning when the schema for your data changes. And finally, explainable predictions can help you understand how different versions of your model are performing by giving insights into the features that lead to those predictions. We can go to the summary slide. So this is just a summary of the 3 patterns that we covered and which chapters they fall into. I'm going to hand it back to Lak for some trivia.
All right. Thank you, Sarah, and thank you, Mike. So as we said, we will be basically doing a giveaway of 5 copies of the book. And in order to do that, we're basically going to be running a little trivia game. So if you have a mobile phone, go to kahoot.it. Now you can do it from a desktop browser, or if you have a Kahoot app, go ahead and, so you just need a browser. So go, if you don't have the app already, go ahead and do the browser and enter this pin. So I will basically wait about 2 minutes for folks to basically open up a browser and add themselves onto it. So we already have 3 people. All right, 19, 20, 22, 25. We have about 100 people on the Zoom, so we kind of know what our target is. And even if you're watching this on live stream on YouTube, go ahead and do that. The way that we will do the book is if you win, right? If you're in the top 5, go ahead and take a snapshot of your screen, right? So do a screenshot and send it to Bill. That is basically a proof that you had this username, right? If for example AN wins, right, An, like basically take a screenshot of you playing the game with the name An, so that we know that it was you. All right. So let's go ahead and do that. We will get started. Okay. So 78. Okay. 80. Good. Okay. So, all right. So this is basically the machine learning design patterns Kahoot. Getting started. 1. All right. First question is just a poll. Are you ready? Right. Just to show you how to use this. We have 26 answers, 30 answers. So on the left-hand side is a countdown, right? So it'll basically count down from 30 to 0. So we have 60 answers. 63, right? All right. So we had 53 people who are ready and 4 people saying, hold on, my friend's still joining the game, hopefully, and 70 people are very confident. Hooray. All right. Quiz starts now. To ensure your model performs well as the data and external trends change, which of these 4 design patterns should you use? Model evaluation, fairness lens, explainable predictions, or rebalancing? All right, 67 people got this right. This was basically on almost the very last slide of Sarah's, where she basically talked about why, right? And continued model evaluation. Perfect, but again, like I've watched this where people come back in the last 2 rounds. So if you didn't get it right, don't give up. Stay in the game. Okay, Asif is leading. Let's go on. 3rd question: when comparing model evaluation and continued model evaluation, model performance, which of these design patterns should you use, right? To compare model performance, which one of these do you need? All right. 59 of you got this right. About 15 thought it was batch prediction. The key thing is that if you're going to be doing continued model evaluation, you have to do this model evaluation as the data are coming in. So it has to be real time. So you can't wait to collect the data and then go ahead and compare models. You have to compare them as the data is coming in. So that basically, okay, now we have a new leader.
Hey, Lak, are you able
Yes.
to control the time? Seems like there a lag on the YouTube. So if you can control, give maybe a few more seconds.
Okay, I can do
end of the questions, so some folks on the YouTube can answer.
Yeah, I mean, if you're on YouTube again, I don't think you get 30 seconds then. Okay. The multi-label design pattern is useful in which scenarios? Okay, this is a trick question. So multiple answers. Okay. It's the multi-label design pattern is useful in which scenarios? What tag to apply to this image? Which city does this bridge go to? What is the bridge built of? And what type of bridge, suspension, cantilever, etc. is this? All right. So all four of these are correct, right? Basically, what tag to apply to this image? It's a bridge, it's water, it's whatever, right? So there's multiple things that are in the image. Which city does this bridge go to? Well, every bridge can be in a city or it can connect two cities. So you might have to have multi-labels there. What is the bridge built of? Well, you have cables that are made of steel and you have concrete on the roadway. So it is possible that you have multiple materials as well. What type of bridge is it? Well, this is where you basically have overlapping labels. So all four are correct here, right? So cool. Okay, next. So Javi Neutral is still in the lead on second. Cool. Okay. Let's do this. To handle categorical features with an incomplete vocabulary, you can use the blank design pattern. If you have categorical features and incomplete vocabulary, which design pattern? So again, now we're going beyond the three that we talked about. And I think I gave you a hint that the red one is not the answer. Okay, so okay. Hashed feature is the right answer, which I don't. Again, this is a pretty cool design pattern where if you cannot one-hot encode your data, what do you do? Because you don't know the full vocabulary, then you can use a hashed feature. So if you haven't heard of this before, definitely a design pattern to know about, because incomplete vocabularies are extremely common, right, in real-world applications. Okay, so now we have a new leader and false. Okay. Feature crosses should be combined with a blank design pattern to avoid the curse of dimensionality. So really, forget about the feature crosses business. Which of these design patterns helps you avoid the curse of dimensionality? Right, it's the embedding, and more of you got this right. Exactly. So remember, we talked about embeddings as a way to basically do dimensionality reduction, right? So that's basically what you do with feature crosses. You basically, even we talked about 500,000 movies, right, and 1 million customers. With the feature cross, you would get 500 million or whatever number of feature crosses. So obviously, you need to do dimensionality reduction there. So An's in the lead. And false, I think the top three are pretty consistent at this point. And Tommy and Justin have just come in. All right. In the rebalancing pattern, blank is an approach to handling inherently imbalanced data sets. Downsampling, upsampling, weighted classes, all of the above. All of the above. Hey, most of you got that. Absolutely. All right. So still Still, okay, the same top 5, with somebody being faster on the draw than the other 4. All right. To create baseline models for explainable predictions, you can use the blank design pattern. Which of these give you a baseline model? All right. Okay. Yes, heuristic benchmark is a baseline model. A lot of people thought it was a neutral class. The neutral class is actually a way of basically capturing maybes. Like lots of times you have yes and no, you have binary classification, but then you will have some things that you're not quite sure of what to label them. And the neutral class lets you handle those in a much better way. So this is not about explainability, it's about uncertainty. Next. So cool, we now have 3 people just coming in, all right. To reuse transform between different machine learning tasks, which design pattern should you use? To reuse a transform between 2 different ML tasks, 2 different ML programs. So this is where you want to do the same kind of pre-processing in 2 different ML models. Right. I mean, transfer learning sounds like it would be the kind of thing where you can basically learn it once and use it somewhere else. But that transfer learning is not about, it's about learning, right? It's not about pre-processing. This is transformations are things like cropping and resizing and things like that. So if you need to apply them to a bunch of different ones, if you want to create an embedding and use the same embedding in multiple places, you want to save them in something called a feature store. So again, another of these really useful design patterns that if you haven't heard of it, you should really like look it up, right? So just do a Google search for feature store. You should be able to find examples of how to use a feature store. A workflow pipeline is definitely part of this, but it is not. No, it's about any kind of reuse, not just about a transform, right? So if you want reproducibility, it's good to have a workflow pipeline. But in this case, this particular thing, to reuse a transform, you want to basically have a feature store. Okay, and okay, Irina has come in. Hooray. Okay, for all the marbles, the blank design patterns are helpful if you want to do fine-tuning. So 2 correct answers. If you want to do fine-tuning is this idea where you have a model that's been already trained and you want to train it again on a new data set, but you just want to fine-tune it. You want to keep most of the original information in it. All right, checkpoints and transfer learning, right? Basically, you need to take the original model, you need to save that out so that you can read it. And typically, you don't save the final checkpoint, you save an intermediate checkpoint because it's more generalizable. And then you basically transfer learn out of that, right? So you need to have both checkpoints and transfer learning. Okay. Cool. And with that, who's the winner? Number 3 is Justin. Again, all of you, for all of these folks, please go ahead and take a screenshot of your screen so that we know that you were the one. So who's number 1? Number 1 is on. Okay, and runners up are Jude and MS2338. So the 5 of you, please go ahead and send an email to Bill so that you get a copy of the book. Okay. And so thank you all very much. We really enjoyed this, and let me just go ahead and turn it back over to you, Bill. And again, just before we do that, right, just links here, how to purchase the book, how to get a free trial to read the book online, Follow Sara and me on Twitter. As Mike said, Mike has a life. He doesn't spend time on Twitter, but the two of us do. So you please follow us. We both have blogs as well. Read our blogs and really